Hello and welcome back. Example 3 says evaluate the integral of the square root of 2x plus 1 dx. So here we're going to try to use the substitution method, and we're going to let u equal the inner function. So the inner function here is that one that we see right inside the radical. That'll be the 2x plus 1. Now, one of the things is when we take the derivative of u with respect to x, we're always moving that dx over to the right. Let's go ahead and just do that on the next step. We're going to write du equals 2 dx. Kind of like back when we learned about differentials and we were treating du and dx as differentials, or dy and dx as differentials, and we just were able to move them around. I think the same thoughts right here. So when we take the derivative, that dx differential can just be moved over to the right. Now the thing is, we don't see a 2 dx to replace, we only see a dx to replace in our integral. So what we can do is take that 2 and divide both sides by 2. We'll have 1/2 du equals dx. So now we can replace the dx with 1/2 du. The integral then becomes, I'm going to write u to the half, so the square root of u would be u to the half. Just get set up for finding the antiderivative. And then times 1/2 du. Now this is a much simpler integral to evaluate, much simpler antiderivative to evaluate. The 1/2 will still stick around. I'll just put that in the front. And then we have u to the 1/2. We're going to add 1 to the exponent to give you 3/2, and then divide by that new exponent. This is how we find the antiderivative. Again, turning back around, if we took the derivative, we would multiply the 3/2 in front, which would cancel with this 3/2, and then subtract 1 from the exponent to give you the 1/2. So that would check out. Now as a last step, if we divide by 3/2, that's like multiplying by 2/3. And if you think about 1/2 times 2/3, the 2's will cancel and you'll get 1/3. So we'll have 1/3 for the coefficient. And then the u we wrote as 2x plus 1. So we can go back to x by writing the u as 2x plus 1. And then we have our plus c. So this is the antiderivative of the square root of 2x plus 1. Again, always double check, especially at the beginning when you're just learning these new methods. Always double check by taking the derivative and making sure that you get back to the square root of 2x plus 1. And don't forget your chain rule. Example 4 says evaluate the integral of x squared e to the x cubed. Now here, if we're looking for an inner function, we can meditate on this a little bit. What would it be? What would our inner function be? If you said x cubed, that would be correct. That's an inner function. That's a function that's inside of the exponential function. And not only that, but the derivative of that, the du, 3x squared dx, basically appears outside. You see an x squared dx. You can move this x squared to be with the dx just by shuffling the factors around. You could have rewritten this as e to the x cubed and then times x squared dx. Now there's not a 3 in front, but that's okay. The 3, as we saw in the previous example, can be divided over to the other side. The main thing is that you have the x squared dx. You need that variable part with the dx to match the variable part in the integral. So now we can integrate here. We're going to be replacing this x squared dx, and I just realized I didn't circle it over here. So to be complete, I'll circle the dx from the previous example. So we can circle this one as being replaced with a 1/3 du. Right, this will become a 1/3 du. And then for the other part, we have e to the u. E to the x cubed became e to the u. Now when we integrate, the 1/3 will be there. The integral of e to the u will be e to the u. And then we'll put our plus c. And as a last step, we'll replace u with x cubed, because that's what u was. That's what you are. That's what you were. That's what you was. Now sometimes you need to do a little bit of algebra before you can make a substitution, before you can do the substitution. So in example 5, we have the integral of dx over e to the x plus e to the negative x. There's a little bit of weirdness in this notation because the dx is right there on top of the fraction. All this means is the integral of 1 over e to the x plus e to the negative x dx. Now if we try to think about like an inner function, I mean I suppose this e to the x plus e to the negative x, that's inside of the 1 over x function if you want to think about it that way. But you know, the derivative of that is going to be like e to the x minus e to the negative x. We don't really see that multiplied to the dx. So as mentioned, we might need to do a little bit of algebra before we can set up for a substitution. What would be really nice is if we had an e to the x there with a dx, because then if we let u equal e to the x, then we'll be set up for a substitution, because the derivative of e to the x would be e to the x dx. So let's go ahead and think about multiplying that e to the x in there. We can multiply the top and the bottom of this fraction by e to the x. Another way of seeing this is taking just one more step. If you think about e to the negative x, that's like 1 over e to the x. Here, just by virtue of wanting to simplify this expression, you could think about multiplying top and bottom by e to the x. But that especially is going to help out because it's going to give us an e to the x to be with the dx. And that's going to be what we can use for our substitution. So here we're going to get integral of e to the x over e to the x quantity squared plus 1 dx. Now what we can do is let u equal e to the x. That's definitely an inner function. That's inside of the squaring function, and its derivative appears with dx. Right? The derivative of e to the x is e to the x dx. Derivative of u equals e to the x is du equals e to the x dx. And we're definitely seeing that here. In fact, I should probably highlight this in red to be consistent. Let me do that. You don't have to highlight it in red if you don't want to, but just to be consistent. So making our substitution, we have 1 over u squared plus 1 du. Now that's a better integral to be looking at. What's the antiderivative for 1 over u squared plus 1? If you said inverse tangent of u, then that's correct. I know that's a tricky one, but that's a really good one to know. It comes up in a lot of examples in future calculus classes, and this one too. One last step will be to replace the u with e to the x, get us all the way back to x, and there we have the answer. All right. Let's check out, we're at 8 minutes and 50 seconds. Let's keep going. Example 6 says, evaluate secant x dx. Now this one is especially tricky because I just lost my notes. Here, there we go. Okay, this one is especially tricky. You can try different things out. You can try rewriting secant x as 1 over cosine x or doing things like that. It's really hard to get a grip on this one, but there's going to be one little algebraic manipulation that's going to help us out here, and it's this. It's a little bit of a trick. We're going to write this as secant x over 1, and we're going to multiply the top and the bottom. Let me write it like this. We're going to multiply the top and the bottom by secant x plus tangent x. It's going to seem pretty mysterious at first, but that's going to really help us out. Okay, so notice what this does to the top. We get secant squared x plus secant x tangent x over secant x plus tangent x dx. The issue with secants and tangents is that we need things that look like this. The derivative of tangent is secant squared x. The derivative of secant x is, blanking for a second, secant x tangent x. This is the mnemonic from many packets ago. Check the video for packet 5 if you have forgotten. So here, these are the derivatives. So we like to see things like secant squared x and secant x tangent x. We like those to be with the dx. And that's what we're going to get when we multiply secant x by secant x plus tangent x. And it so turns out that what we're going to get on the bottom of the fraction is the function whose derivative is the top of the fraction. Look at the derivative of secant x plus tangent x. The derivative of secant x is secant x plus secant x tangent x. The derivative of tangent x is secant squared x. And so the derivative of the whole bottom is the whole top. So this is going to be perfect for substitution. We just set ourselves up for a perfect substitution. We're going to let u equal secant x plus tangent x so that the derivative, the du, is secant x tangent x plus secant squared x dx. And I should have written that in red again. I gotta stop doing that. Let me try that again. Fast forward through this part. Okay, there we go. So the entire top is going to be replaced with du. The integral will collapse into just 1 over u du. And that's much easier than this whole convoluted setup that we created here. Because now the integral of 1 over u is ln absolute value of u plus c. And then we just go back to x. We replace u with secant x plus tangent x plus c. So the integral of secant x, it seems a little bit benign, but it actually ends up being a fairly complicated antiderivative. It's ln absolute value of secant x plus tangent x plus c. Again, turn back around, take the derivative of this, and show to yourself that you end up getting secant x. All right. So example 7 is evaluate the integral of x times the square root of 2x plus 1 dx. And here, just about the only inner function that we really see here is 2x plus 1. 2x plus 1. The only thing is that the du would be 2 dx. And we don't really see a 2 dx. We see an x that could go with the dx, but not a 2 dx. It looks like the variable part is not really matching here. But in this particular case, it doesn't always happen this way, but in this particular case, we're going to be able to get out of this in just a moment. Let's take the 2 and divide it over, since we don't see a 2 at all in the integrand. So we're just going to be replacing the dx right here. We're going to replace the dx. So we have the integral of, well, we have the square root of u, right? And then we have the dx, turns into 1/2 du. But then the problem is, what do we do about the x? Our new integral has to be all in terms of u for this to work. We can't have mixed x and u inside of an integral. It has to be all with respect to just a single variable. Well, to deal with the x, what we could do is use this original setup that we had between u and x. This was the arrangement that we set up. We could solve this arrangement for x in terms of u. We can subtract the 1 over and then divide by 2, and we'll get x equals u minus 1 over 2. So that's what we can replace x with. We can replace it with u minus 1 over 2. Now you can always do this as long as you can solve for x, but it's not always going to help out. It's just that in this particular case, it does help out. The reason it helps out is because it shifts the plus that was inside the radical into a minus outside the radical. And that makes it much better because we're going to be able to distribute this square root of u into each of these terms, the u and the minus 1. And then we can integrate separately. We can integrate term by term. We couldn't have done that originally because there's no way for this x to distribute into the 2x and the 1. Plus, you have the two terms guarded by this radical. It makes it very difficult to find the antiderivative. So let's take a moment to simplify this a little bit. We're going to take the 1/2 that is part of this first fraction times the 1/2 that's part of the second fraction. And something I haven't done before is pull that out of the integral. So you can take a constant and pull it out of the integral. Just like you can take a constant and pull it out of a derivative, you can do the same thing with an integral, because the integral, again, is an antiderivative. And so a lot of the same kinds of properties apply for antiderivatives that apply to derivatives. Then we're going to take, let me write this off to the side. We're going to take the u minus 1 times the square root of u and distribute that square root of u in. Remember that the square root of u is like u to the half. So when it distributes in, you'll get u to the 1 plus a half, which is 3/2, minus u to the half. So this becomes u to the 3/2 minus u to the half. Oops. du. Now we're going to integrate term by term, or find antiderivative term by term. So here we're going to use kind of a, not really a trick, but just looking one step ahead. Here, if we find an antiderivative, we're going to add 1 to the exponent, which gives you 5/2. Adding 1 is like adding 2 over 2, right? It's like you're taking the denominator and putting the same thing on top and bottom of the fraction to rewrite 1. So you're basically adding the denominator to the top to get 5, and then you still have a denominator of 2. That's a little trick to adding 1 to the exponent. You're basically adding the denominator to the top to get 5 here, and then keeping the denominator the same. Now dividing by that new exponent, dividing by 5/2, is the same thing as multiplying by its reciprocal. So that's times 2/5. So a lot of times when we're doing this, especially the farther on we go, we're going to be doing this kind of a trick to save us time and to not have this divided by a fraction business going on. Dividing by a fraction, we know, is like multiplying by the reciprocal. So we might as well just go right to it. Let's think about that same trick here for adding 1 to the exponent. So 1/2 plus 1, to add 1 to this fraction, we're just going to add the denominator to the top to get 3/2. Oops, got to write the u first. So 2 plus 1 gives you 3. We have the same denominator. And then when you divide by 3/2, that's like multiplying by 2/3. Okay. Now I use brackets, but you can also use parentheses. Either way. I'm going to change these to parentheses, actually. There. Looks a little bit nicer. Less rigid and pointy. Okay, so the only thing left to do is simplify. So we're going to distribute the 1/4. That'll cancel off with a 2 and give you 1/10. We're also going to replace the u's back with 2x plus 1 to the 5/2. Then we have 1/4 times 2/3. The 2 will cancel. We have 2 times 3, which is 1/6. And then again, going back to x plus c. Okay, so that concludes this video. Gracias, and see you next time.